Okay, so I want to talk about something that I find very fun, and to show you how to get started and then show you some examples of Monte Carlo calculations. So this is basically the idea of solving problems with random numbers. So here I have a picture of dice. We roll dice in random, so that's my example. Okay, so let's start with the idea of a Monte Carlo calculation first of all. So this is Monte Carlo. It's a city, and this is what it's named after. This is the Monte Carlo casino, and that's where the name Monte Carlo comes from, because of gambling and stuff like that. And so I think there was some ideas about it originally being a code word, so they wouldn't know what was going on. Some probably to do with World War II or something. I don't know. I don't know all the history. Let's just get into a Monte Carlo calculation. I want to start with my favorite Monte Carlo calculation of all time, and that's using Monte Carlo to find the value of pi. So imagine that I have this part of a circle, and I'm using a part of a circle, and you'll see why in just a second. If I have a quarter of a circle like that with the radius r, then it would have an area, and I'm calling it area 1 because there's going to be an area 2, of a fourth of the area of a circle. So the area of a circle is pi r squared, so this is pi r squared over 4. Okay. Now, imagine I have a square, and this square has dimensions r by r, so it matches up with the semicircle. And that has an area of r squared, right? Now, what if I put these two things together, just like that? And now I can generate random points, okay? So I could generate a random point right there, r1. How would I do that? Well, I would say it has some random number for the x coordinate, some random number for the y coordinate, and so it's a vector r1, it's some random number. Now, that random number is inside a circle. I could also generate a random number where I have r2, it's also some random number. And here's the deal. I can say if I generate random numbers in this box, and so they're r by r, I mean 0 to r, and 0 to r in the x, y. If the magnitude of the vector is less than the radius of the circle, which r1 is and r2 is not, then I can say, okay, that's a circle. That's in the circle. And if it's not, then it's not in the circle. And so the point here is that the ratio of random points inside the circle to the total is the same as the ratio of the areas. Oh, and I should point out, this is how I am using GlobeScript Web VPython. And in this Python, we can make a random number with the random function built in. This just returns a number between 0 and 1. It's a random number. Okay, so if I do that, then the ratio of areas is equal to the ratio of the points in and total. And so then I can just say the number of points in the circle divided by the total number of points should be pi over 4. Let's do it. Okay, so here's my actual code. I have a link to all of my videos using Monte Carlo calculations, a playlist, and I'll put that down below so you can go back and look, and all those have codes and everything, so all the code's there. Okay, let's just go over some of the important parts of this code, and this is in Python. If you're not familiar with Python, I don't think it's a big problem. So the first thing I do, and I do this the way that I try to make sense with students, right, because I try to use Monte Carlo calculation for students, is to have these counters. So here I'm saying n is 0, that's the number of total points, and nc is the number of points in the circle. Okay, and then what I'm going to do is just make 10,000 points. So I'm going to have while n is less than 10,000, do everything in this loop. And that's what I'm going to do. And then what I do next is to generate a random number. I need a random x coordinate and a random y coordinate. The rate right there, that just makes it run at a certain speed, so it's not that big of a deal. And then after that, I'm going to calculate the distance from the origin, and I'm going to call that r. It's just square root of x squared plus y squared. That's how you find the magnitude. And then I'm going to say, if r is less than 1, then count that as a circle point and make a plot, right? I have 2 points that I'm plotting. I'm plotting 2 curves, and they're different colors. And then otherwise, plot it as outside the circle, but still, either way, count the total number of points. And then I can use that total ratio of the number of points in the circle to the total number of points, multiply it by 4, I get pi. That's that. So here's what it looks like. This is an animation of how that would work. This isn't all 10,000 points because I got bored of watching it run. But you can see how these are just random points. And you can start to see the circle there. And I think that's pretty amazing, right? Because we don't have any pi in our calculation. We don't have cosine. We don't have any trig functions. It's just random numbers, and we're using the square root. And so from this, I calculated pi as 3.1388. So it's not the best value of pi, but it is a value of pi, right? So that's significant. Okay, so what if we want to use Monte Carlo to calculate something else? What if I want to calculate the moment of inertia for a disk? So this is a disk, has a total mass m and a radius r. How would I calculate the moment of inertia? So we define the moment of inertia as, if I have finite points, it's the mass of each point times its distance from the axis squared. And this is the scalar version of the moment of inertia. If I have a continuous medium like a disk, then I'd have to integrate. And I put the double integral there because we're integrating over the area, right? So it has to be some type of double integral. And it'd be the radius of each point and the mass of each point. And so the dm is our integration variable. We have to figure out how to get that into space coordinates to integrate over space. And if you did that, the moment of inertia would be 1/2 mr squared. And it's not a super hard problem to do. There is a trick, and I'll show you the trick. But if you just start from scratch, it's not trivial. So why is it not trivial? Well, let's think, how would I break this up and do the area of a circle and integrate over the area of a circle? Well, the first way would be to use Cartesian coordinates. If I use Cartesian coordinates, then I'm going to break these into little x pieces and add up all the pieces in the x direction. And then once I get that row, repeat it down again. That's easy to integrate. But the limits of integration depend on x and y, right? So as I move down in these rows right here, my boundaries change. And so you have to take that into account. It's not impossible, but you have to do that. So that's not, that's something to consider. And remember, we do moment of inertia in introductory physics courses, and this isn't something that we really want to get them into too much right away. Okay, so the other obvious thing is to use polar coordinates, right? So I can use polar coordinates and integrate around theta from 0 to 2 pi and r from 0 to r, and that's fine. But then I have to have this area element. The area element in Cartesian coordinates is very easy, right? It's dx dy, multiply that by the area mass density sigma, and that's how I get this down here. Now in Cartesian coordinates, we have this sigma r dr d theta, and why is it that way? We know why, but it's hard to explain to a student, especially an introductory student, why that's the case. Okay, so then there's another way, and this is the way. Oh, I covered up my face. That's fine. That's fine. My face is more important than the dm. Okay. But this is the way that I do it in introductory classes. If you can find the moment of inertia for a ring, which is really easy, then you can just add up a bunch of rings. It's really a one-dimensional integration, and that's pretty easy to do. Okay, so those are the 3 ways to do it. But there's another way to do it. I could take this circle, generate random points, and each of those points has mass, each of those points has an r vector, and then calculate the moment of inertia by summing up the points. And again, representing the points as an area. So here's another point. They're all, I just randomly picked those aren't real random. I did those. And then the moment of inertia would just be the sum of m r squared for each of those points. But you have to be careful, right? That the mass of each of those points is the total mass of the disk divided by the number of points that you have. And that would be important. But they'd all have random points, and that'd be fine. And this can work fine. But the question is, how do I make random points in a circle? That's not quite trivial. It's not impossible. Okay, so let's look at 3 ways you can make random points in a circle. The most obvious way would say, well, the r can go from 0 to 1, or whatever the radius of the circle is, and theta goes from 0 to 2 pi. So I could just do that. I could say the r is some random number, 0 to 1 times the radius of the circle, I call that capital R. And theta is 2 pi times 0 to 1, so it could go from 0 to 2 pi. But if you do this, it does not work. You get this distribution of points. This is like 3,000 points right there. And you'll notice that they're clumped more at the center, right? Because as theta moves around, that spreads those points evenly around the circle, but now you have a bigger circle to spread those points around. So as R increases, the density decreases too. So this is not a uniform point distribution, and if you use this to calculate the moment of inertia, it's going to be wrong. Okay, so here is another option. This is, it's the wrong picture. Well, if I take the square root of R, it does work. Okay, then I actually get this. I do get a uniform distribution, and it's not clear why. I mean, it's not easy to explain why that's the case, but that would work in this one particular case. But I wouldn't recommend that to students because it's just a trick to get the random distribution. But you can still have theta go from 0 to 2 pi, and then R is the square root of a random number. Here's the way I like to do it. It's with the Cartesian coordinates. So imagine that that one's wrong. Okay, there. So imagine that I generate a random X number and a random Y number in a box. Okay, so here's a little trick here. So the random function in Python returns a number between 0 and 1. So if I multiply that by 2 and subtract 1, I actually get a number between -1 and 1. So this gives me, this box is actually a little too big. No, it's not. So this gives me a box from -R to R in the X direction, -R to R in the Y direction, and there you see those points. But it's not a circle. So what I want to do is to take each point, and if it's not in the circle, throw it away. And I can do that with this function right here. So here's my counter in less than some number that I want to count up to. I generate a random number right there in 38. That goes in a square. It's no z component here. And then I say if the magnitude is less than R, then I draw a sphere. And I add 1 to the counter. And if it's not in the sphere, in the circle, then just throw it away and just start all over. Okay, if you do that, those yellow points are what it would look like if I only take the ones that are in that circle. But now I have a uniform distribution of numbers in a circle, or points in a circle, and I could use that to calculate the moment of inertia, and everyone would be really happy. But if you have points in a circle, you can also do things like the electric field due to a circular disk. And this is what it looks like. So there's my disk, a whole bunch of points. I calculate the electric field at all these different points. The distribution of points is the same. The only thing difference is the physics, right? So here I have a red point charge, and the white point is where I want to find the electric field. So I have a vector location for the charge, a vector location for the observation location, and the vector from one to the other. That's what I want. And imagine that I break that disk into 1,000 points. It could do that. Then Ri, the vector for each one, is just the observation location minus the charge location, and then I can use this to calculate the electric field due to that 1 point charge. And then I just add up all the electric fields, and I get my total electric field. Okay. What about three-dimensional objects? So I can make a three-dimensional sphere. This is a three-dimensional sphere. Okay. And I'm going to zoom in just so you can see that there are points on the inside too. So this is like, 3,000 points or something like that. So how would you do that? It's not that hard. If you can make a circle, you can make a sphere. There's no difference, right? So this is just generate a cube of points in 3 dimensions. So now I have 2 random minus 1, 2 random minus 1, and so forth. Did I do those other ones backwards? It is 1, should be 1 minus. I did 2 times random minus 1. No, it works either way. And then I just find the magnitude of that vector is the same thing. I just don't have a z component of 0. That's it. And so if it's in that radius, then make a point. If not, then don't make a point. Easy. So in this case, I'm using these points to calculate the electric field due to the sphere, and to show that you get the same electric field as if you assume there's 1 point charge in the middle, and it works pretty well. So there's my theoretical electric field, my actual electric field. You'll notice that it's 6.7 times 10 to the 7th in the x direction, which it should be. I had my point in the x direction. And the other ones are much smaller, even though it's times 10 to the 5th. It's really small. Of course, the more points you have, the better. But again, this is not the best way to calculate the electric field, but it is a great way to show students that a uniform distribution of point charges looks like a single point charge. That's the point. What if I want a shell of charge? Here's a sphere, but there's nothing in the middle. So if you zoom in, you can see there's nothing in there. Zoom back out. So it's a hollow sphere. So in this case, what you need to do is to pick the thickness of that shell, right? So I call it dr. So right here in line 23, it says that if the magnitude is less than r and greater than r minus dr. So now I have some thickness. So again, I'm just eliminating, I'm only picking the points that fit my criteria. If not, I throw them away and I start all over. So you make a lot more points, but you only care about the ones that fit the criteria. And you end up with a uniform distribution along the shell. And then you can calculate the electric field due to that. You can calculate the electric field inside that and show that it's approximately zero. That's kind of cool. The uniform charge distribution of a sphere, the electric field is zero on the inside. This is the moment of inertia tensor. This was a problem I did in a class for a cone. And it turns out that you can do it and you can do the calculations, but it gets really difficult to integrate over a three-dimensional cone, especially when you need to find a tensor like that. So instead, just do a numerical version, a Monte Carlo version. So I did a Monte Carlo version, same idea. Once I have the criteria for what would be a point in the sphere, in the cone versus not in the cone, then I can generate random points and throw away the ones I don't want. And that's what I'm doing right here. So this line 18 says, if my temporary vector, if the z component is less than h, I cut off the bottom. And then this is cut into a circle. And then, what did I do? Oh, and then, I can't remember actually how I cut that, but you could come up with a criteria for how to cut that. And I'm actually calculating the moment of inertia tensor about that yellow point over there. So it'd be something that'd be really difficult to do, if possible at all. But with the Monte Carlo calculation, it's easy. Okay, and you don't have to worry about how to literally cut that into pieces and to do a volume integral. I can just randomly make the points. Okay, let's look at flux. So we have electric and magnetic flux. We define flux as E dot n hat dA. So what's E and what's n hat? So if I have some cyan arrow right here, that's my electric field, and the yellow arrow is the unit vector perpendicular to this area, then I can calculate the flux for that little piece of area. Okay, but the problem is, what if you want to do like curved surfaces? What if you want to do changing fields? What if you want to do a changing magnetic field? Then how would you find the flux? And you can break this into regular patterns. I've done that before. It's a lot of fun. So let's look at the magnetic flux through a ring. So suppose I have a moving charge and I want to calculate the flux through a ring. Well, I need to break that into, again, random pieces, but I don't want to use points because I need to know the orientation of each of those pieces of my ring. In this case, they're all in the same direction. So what I do here is I make a temporary vector in a circle, right? So there's my temporary square in line 27. And then in line 28, I just take the circle points. And then what I'm going to do is add each of those points. I'm going to make a cylinder and add it to a list. That way I can go back and calculate stuff based on those things. The nice thing about the cylinder is that it has an axis that tells me the orientation. So in this case, the orientation, I have two important things here. Number one, it's in the z direction, right? Because if I have my disk, I'm going to show you the picture. Actually, this is it right here. So there's my ring right there. There's my moving charge, and these are all my pieces of my random pieces of the area, that the flux. I need the total area of all these to add up to the area of the ring. So that's what I need to calculate that. And then this is the z direction towards me. So they all have an axis in the z direction. So now I can use that vector for my n hat to calculate the flux. And this is how you would calculate the flux. You'd go through each one of those areas, and I could just do right here d flux. That's where I calculate the flux due to each piece, and then I add that to the total flux, and I use the dot product. That's it. Okay, so it works really well. What if it's not? What if it's not flat? I can still use these disks. So here's the flux through a hemisphere. I really like this picture, and I actually drew all the areas, the arrow vectors, even though you don't need that. Every cylinder, these do add up to the total, but some of them overlap. Okay, so it's not the best. It's not the best, but it does work. Of course, if you have more pieces, they cover better, but they never cover completely. But it still gives a really good value for the flux this way. Here's how I would do that. So I calculate a random variable, and this is in three dimensions, and then I need to cut out. I make it into a shell, the same thing, but I make the y components greater than 0, so I cut the bottom half off. Now, instead of just putting a sphere there, I put a cylinder, and you'll notice here this axis is important. That's the orientation of the cylinder. It's the unit vector for the location, and that makes sure that they all are pointing away from the origin. And now I have that when I calculate the flux, I can get it all to work. What if I wanted to do a cylinder? Here's looking at a cylinder, okay? And again, you have just a finite number of pieces. The total area adds up to the total area of the side of the cylinder. In this case, I again start with a cube, okay? I shifted them all up so they were above 0. That was for another reason. And then I just eliminate the ones that aren't in that shell. So I need the xz component. I want it to be the radius from the z coordinate, from the y coordinate. That's what this is rotated. So you can get them all like that, but then again, I need that unit vector pointing away from the surface. And once you make that, you have a pretty complicated surface, and I can calculate the flux. Each one of those cylinders has an axis, and I can calculate the flux if I have a field. And the field doesn't have to be constant. I can have the field at all these different locations. It's pretty nice. Here I could do the same thing for a cube. This is actually what I did was to randomly make each of the 6 sides separately, right? So I would just randomly distribute in the x direction or in the xz plane, and then the xz plane plus some constant and so forth. So I have 6 sides, but each one of those tiny cylinders in there has the correct unit vectors, and then I can calculate the flux really easily. And this is kind of easier than trying to figure out how to break these into patterns and stuff like that. It's not perfect, but it's easier conceptually to understand what's going on. Okay, one more example. This was a problem. It was a bad, I didn't like it. Okay, so the physics problem was this. There's 2 charges down here, Q and Q, and the question was, where could I put a charge? And there was another charge right there. I think there was another charge right there. I can't remember. And the question is, where could you put this charge so that the electric field is 0? No, that's it. Where do you put this charge such that the electric field is 0 right here? So I have the electric field due to these 3 charges. And I mean, it's not a trick. There's a couple tricks you can do to solve this, and I do solve the problem. But I'm like, it's just a dumb problem. We could solve this with a Monte Carlo calculation. If I know the approximate location of where the point should be, what I can do is just put it in a whole bunch of different random points until the electric field is 0, and that's the answer. So here's how to do that. So here I have 10,000. I'm gonna make 10,000 points. I'm gonna this R temp just makes them in that little sub area over there where I think the electric field should be 0. This is a function that calculates the electric field due to that new charge. I already had the electric field due to the other ones. And then I'd say if it's less than some value, if the magnitude of the electric field is less than some value, then it's close to 0. And I'm going to plot a red point. Otherwise, I plot a blue point. And here you get the following results. So you can see I got a couple of solutions right there showing you where the electric field is 0. If you wanted to do this as a problem that you couldn't solve, you could then take those vector values and make a smaller box and do it again. You could keep doing it until you get a smaller and smaller and a more approximate answer, and use Monte Carlo like that. So here you see all the points that did not have a close to 0 electric field, and those 2 did. So it's kind of a fun way to think about solving problems, right? I'm just going to pick some random numbers and see if it works, and just pick some more random numbers. Okay, so I hope that helps you get started with the idea of Monte Carlo calculation. Again, the playlist down below, if you have any questions about any of the particular calculations, let me know. If you want to watch all the old videos, you can see how to do it in Python. But I like to have fun with these Monte Carlo calculations. I think they're quite fun. So that's that.